In this set of notes, we're going to start looking at small confidence intervals for mu and mu1 minus mu2. So in other words, we're looking at sample means either from a single sample or a difference in two means from two independent samples. And so a lot of this should be review. You've probably looked a lot at small sample confidence intervals in some of your previous intro courses. So again, we've been using the central limit theorem, which works for any population, but it does require a large sample size. So for example, if we're estimating a population mean, a sample size of at least 30 is generally sufficient. You all actually looked at that in your second mini project. So suppose that we want to find a confidence interval for the population mean mu and the variance sigma squared is unknown. If we do not have a large sample size, in other words, we have less than 30 in our sample, there are several problems here. The first of which being that the distribution of the sample means may not be normal and S may not provide a good estimate of sigma. So to solve these problems, we're going to add on a couple additional assumptions about our data. We are going to assume that we have a random sample from a normal population with mean mu and variance sigma squared. And we've looked at t distributions in the past, and so we're going to utilize t distributions here. So note that the t distribution is also used when sigma squared is unknown and the sample size is large. For large enough samples, there is little difference between the quantiles of the t distribution and a standard normal. So here are a couple facts on different confidence intervals that we could look at. And the main difference between these and what we've seen before is instead of using the quantiles from the normal distribution, we're now going to use the quantiles of the t distribution. Alright, so let's look at an example. So a random sample of 20 police officers subjected to constant inhalation of automobile exhaust fumes has a mean blood lead level concentration of 29.2 micrograms per deciliter with a standard deviation of 7.5 micrograms per deciliter. Further, the sample data were approximately symmetric and unimodal with no outliers. So looking at a couple of pieces of information here, notice that our sample mean, or x bar, is equal to that 29.2 and our sample standard deviation is equal to 7.5. The other important information is we're willing to make this assumption here that the sample data is approximately symmetric and unimodal with no outliers. So if our sample data looks like this, really what we're doing is we're making an assumption about the population, and we're saying that the population is probably normally distributed. So the first thing we're going to do is we're going to construct an appropriate 95% confidence interval for the mean lead level concentration of all police officers subjected to constant inhalation of automobile exhaust fumes. Alright, so in order to construct this confidence interval, we need to make sure that certain assumptions are met. And so remember that one of those assumptions that we made is that the population distribution is normal. And so this is again why we need this highlighted piece here, so it's fine to move on with these methods. Now, one thing to note about the t distribution, it is not a fix-all problem. If it's not reasonable to assume that the population is normal and you have a very small sample size, the t distribution may not be appropriate to use to construct these confidence intervals. Alright, so to construct the confidence interval, notice here we are going to create a two-sided confidence interval. So in other words, we're looking for this one right here. So just writing down our formula, we're going to have y bar plus or minus t, and then notice the t that we're going to want here is a t alpha divided by 2. And usually with the t, when we look here, there really is a degrees of freedom on there with that. So our degrees of freedom, if you'll remember, is going to be n minus 1. So we want n minus 1 degrees of freedom. See, that's right here. And then further, we need to write down the standard error of y bar, which, looking again here at our formula, is s divided by the square root of n. So looking at all of our pieces, we know that our sample mean, notice here, we've denoted in the formula with y bar, but that's the same as x bar. So we have 29.2. Now next, we're going to need t alpha divided by 2. So where that comes from is if we were to draw a t distribution, which is centered at 0, with 19 degrees of freedom, what we're saying is if we place 0.95 or 95% of the area in the center, our critical value is going to be at this endpoint. So we can use R to help us find this. We would use one of those Q functions. So we'd use QT of 0.975, comma 19 for 19 degrees of freedom. Now remember, the reason we have 0.975 and not 0.95 is because the area to the left of that endpoint that we are interested in has the 0.95 plus this bit of area right here, which is equal to 0.025. And so if you put this in R, this is equal to 2.09. We'll go ahead and take that out 2 more decimal places, 30. Our sample standard deviation was 7.5, and again we had 20 in our sample. So the next thing you want to do is put this in your calculator. And I got the following. We've got 29.2 plus or minus 3.5101. And then again, we could put that into interval form. So on the upper end, we're going to get 32.7101. And then on the lower end, we get 25.6899. And then we can interpret this interval in context of the problem. So to interpret this interval, we would say we are 95% confident that the mean, and going back into the context of our problem, remember here that what we're interested in is the mean blood level concentration. And we were specifically interested in police officers. And remember, if we go back up here, we're looking at police officers who were subject to constant inhalation of automobile exhaust fumes. And then is between the interval that we found. And our units of measurement here, if we go back up, were micrograms per deciliter. So that would be a confidence interval for a single mean. We can do something very similar for the difference of two means from independent samples. So again, we're going to relate this to the t-distribution, but there is one difference here. So the problem is, if we try to standardize x bar minus 1 bar, y bar rather, or in other words, the difference between those two sample means, part of the problem is that we don't know sigma 1 squared and sigma 2 squared. So if we go and make the further assumption that the two population variances are equal to one another, then we can construct this confidence interval where we have a pooled estimate of the standard deviation. So notice we're adding on an additional assumption. We are going to assume that each of these come from normal populations, but we further have to make an assumption about the equality of the variances in order for this to work. Now, you have probably seen, in your statistics courses, there are other formulas that look at ways to estimate or to take care of this problem. So this is by no means the only way to handle this problem. It's just for here we are going to make that assumption that those two population variances are equal. And then we have our formulas for our confidence intervals. And here's a note on our degrees of freedom for our t-distribution. So again, most of this should be review from your intro statistics course. You're just now seeing where these formulas are coming from, and they're motivated by all the things that we've seen previously. So again, we can look at another example. So our example says, does cocaine use by pregnant women cause their babies to have low birth weights? To study this question, birth weights of babies of women who tested positive for cocaine during a drug screening test were compared with the birth weights for women who tested negative. The birth weights are measured in grams, and it's assumed birth weights are normally distributed, and here we have a summary given below. So remember that in order to construct our confidence interval, there are those assumptions that we need to meet. The first is that our population distributions are normal. So here we're making the assumption that birth weights are normally distributed, and we don't make the distinction between those born by pregnant women who use cocaine and those that do not. So we're just assuming in general babies' birth weights are normally distributed. So for our two independent populations, those corresponding population distributions, we're going to assume they're normal. The other thing that we need to assume is equal population standard deviation. Now, when you take samples from two independent populations, the likelihood that those sample standard deviations are going to be exactly the same is pretty much zero. But our question is not about whether or not the sample standard deviations are equal, it's whether or not the population standard deviations are equal. And we know that when we take samples, any statistic is going to have some variability. So generally what we're looking for is those two sample standard deviations to be somewhat close to one another. So if we look here, our standard deviations are 599 and 672. Those are relatively close to one another. Some texts will suggest as long as one is not twice the size of the other one. I've seen 1.5, I've seen 2.5, so there are different kind of general rules for that cutoff. But here these are relatively close, so we are going to make the assumption that the two population standard deviations are equal to one another. So just like before, we're going to start with our formula to find a 95% confidence interval for the difference in the mean birth weights. So our formula is going to be as follows. We're going to take x bar minus y bar plus or minus, and coming up here, notice this is going to come from this formula right here is what we are looking at. So I'm going to have T alpha divided by 2. I'm going to have my pooled variance times the square root, and we've got again 1 over m plus the square root of 1 over n, where those are our two separate sample sizes. And then we're going to also need to calculate that pooled standard deviation, or our pooled variance. So here we're given the formula for the pooled variance, so notice when we plug that in, we are going to need to convert it to the standard deviation. So in order to do that, I'm going to go ahead and take the square root of that value that we have the formula for. So writing down that formula, we're going to have m minus 1 s1 squared plus n minus 2 s2 squared. And then in the denominator, you'll notice we're also going to have n minus m plus n minus 2, which that also gives us the degrees of freedom for our t distribution. Okay, so let's identify what some of these different values are. So we're going to let the positive test be group 1 and the negative test be group 2. So looking at our means, here we're going to have x bar, here we're going to have y bar, here we have s1, here we have s2, and here we have m, and here we have n. So now we have all the pieces that we need to plug in with the exception of T alpha divided by 2. So again, that is going to come from a t distribution, which is centered at 0. The degrees of freedom are going to be equal to m plus n minus 2. So in other words, 13 plus 18 is going to give us 31 minus 2. So we're going to have 29 degrees of freedom on our t distribution. We're making a 95% confidence interval. So in R, you want to use QT 0.975, 29. Placing that in R gives 2.0452. So now we have everything we need to plug in the formula. So take just a moment and do that. Pause the video and come back, and I'll tell you what you should have found for the interval. For the calculator, for the confidence interval, I got 450 plus or minus 478.51. Alright, so next our question is, based on the interval you obtained in Part A, do you think the cocaine used by pregnant women caused their babies to have lower birth weight? Explain. Well, a couple key words here, but before we dive into that, let's actually write this out in interval form so we can look at it. So looking at our lower bound, we're going to have 450 minus 478.51. So we're going to have, oops, sorry about that, negative 28.51. And then on the upper end, we're going to have 450 plus 478.51. So we're going to have 928.51. So notice that our interval does contain 0. So with 95% confidence, it is plausible that the two birth weights are equal to one another. The other thing to note here is the word cause. We always want to be careful anytime we're trying to prove causation. In order to prove causation, we are going to need a well thought out experiment. We need to make sure that we account for confounders. There's a lot of things that goes on into actually proving causation. So not only does our confidence interval suggest that it's possible there is no difference between the birth weights, in addition to that, we need to be careful about how that study was set up to ensure that we can actually, say anything about causation at all. All right, so the last thing we're going to look at here is confidence intervals for sigma squared. So again, previously we talked about how that sample standard deviation or sample variance is an unbiased estimator of the population variance. So here, I'm just going to go ahead and give you what that confidence interval is. One thing to note, this confidence interval is going to use a different distribution than the confidence intervals we've looked at previously. This is actually going to involve a chi-square distribution. So one thing to note is that when we found 101 minus alpha confidence intervals for mu and mu1 minus mu2, we also had to assume that we had random samples from normal population. However, if our data were not normally distributed, we still have confidence. Oh, that's an error there. That shouldn't say coefficients there. We still have confidence that we will be close to the central limit theorem. And so that's if, our sample size was reasonably large, we could do that. Now, if our sample size is small, we may not be able to invoke the central limit theorem. Now, when we find confidence intervals for sigma squared, though, the true confidence, and again, I just want to get rid of the coefficient there. Actually, in this sentence, I think it's fine. The true confidence will not be that 100 times 1 minus alpha percent if our data are not normally distributed. So we have to have that normally distributed assumption here when we look at confidence intervals for the population variance. All right, so let's look at one example here. So in laboratory work, it's desirable to run careful checks on the variability of readings produced on standard samples. In a study of the amount of calcium in drinking water undertaken as part of a water quality assessment, the standard sample was run through the laboratory 6 times at random intervals. The 6 readings in parts per million were as follows. We're going to estimate the population variance for readings on this standard using a 90% confidence interval. So the first thing we need to do is confirm, is it reasonable to make the assumption that that population distribution is normal? And so we can do this by assessing what our data looks like. So here I have a normal QQ plot looking at our data, and we can see that our sample size is small, but looking at our QQ plot, I'm not very concerned. So I think it would be reasonable to continue with this assumption. So, writing down our formula, we're going to be using this formula right here. So we have n minus 1 s squared, and then in the denominator, we had chi squared with alpha over 2. And then on the upper end, we still have n minus 1s squared, but now we have chi-squared 1 minus alpha over 2. Alright, so in other words, what's really going to change our upper and lower end is where we are with our chi-squared distribution. So on the lower end, we're going to be using this endpoint on our chi-squared distribution, and on the upper end, we're going to be using this value. So first thing we need to do is we need to identify what our different values are. So n in this case is going to be our sample size, so we had 6 readings. We also need our sample variance. So our sample variance in this case is going to be equal to 0.0286. And you could use R or a calculator to find that. And then we need to find our 2 different endpoints. So the first one we're going to find is the chi-squared alpha over 2. So again, you would find these using R. Now here we want to make a 90% confidence interval, so let's see how to find these. So the chi-squared alpha over 2, for this one you're going to want to use Q chi-squared, so similar to what we saw before when working with the chi-squared distribution in R. And since we're making a 95% confidence interval, we want 0.05 area to the right, or pardon me, to the left, and then we're going to give it our degrees of freedom, which are going to be n minus 1, which is 5. So remember that the notation here and what we put in R is slightly different. So when I put in 0.05 in R, that is going to be looking at the area to the left. So putting that in R gives us the following. We're going to get 1.1455, and then getting the other endpoint, we're going to put in 0.95. That's going to give us 11.0705. Now, one thing that I recommend is don't pay too much attention to the notation that is down here at the bottom. And the reason I say that is some notation will use this as alpha divided by 2 area to the left, and some will use it as alpha divided by 2 to the right. So it's better just to remember conceptually what it is you are looking for. So in this case, we know that we're looking for the 2 endpoints that correspond to having 0.9 in the middle. So that way when we go to use R, that's how I know the 2 endpoints that I'm going to need for my interval. So that's going to be this one, and this one is going to be this one. And then when I go to put them in the denominator for my confidence interval, I know if I put a larger number in the denominator, I'm going to end up with a smaller number. So I know that this endpoint has to have the 11.8705, and this endpoint has to have the 1.1455. So then placing those into the formula, we do get the following interval. And this gives us a 90% confidence interval for the population variance. And this is going to end this note set.